Student friends, in yesterday's lecture we studied class AB push-pull power amplifier and we concluded that class AB push-pull power amplifier is used to avoid the crossover distortion which is present in the class B push-pull power amplifier. Class AB push-pull power amplifier is a power amplifier in which output collector current flows less than positive and negative half of the AC input cycle. Its operating point is adjusted in between the class A and class B. Efficiency of that particular class AB push-pull power amplifier is also lies in between class A and class B. Friends, now we are simplifying these push-pull power amplifiers by using some another aspect, and that aspect we can call it as it is the complementary symmetry type of power amplifier. Student friends, the name itself is going to suggest that the circuit is symmetrical and the working of this circuit is complementary to each other. So that's why the circuit which is used to amplify the input power presented here, it is called as the complementary symmetry power amplifier. Such a power amplifier is used only to avoid the disadvantages present in either class A or class B push-pull power amplifier, and that is in class A, class B and also in class AB push-pull power amplifier, all of these makes use of the input transformer and output transformer. The input transformer is used to provide 180-degree out of phase input signal to be amplified to the base of both the transistor. That means it is the input transformer used to drive the base of both the transistor by providing 180-degree phase shifted input signal to them. At the output also it makes use of another transformer known as output transformer that is used to deliver the maximum power to the load so as to drive that particular load. Assuming two transformers are used, the circuit of class A, class B and class AB push-pull power amplifier becomes bulky, or we can say it becomes heavy. There is rise in cost that takes place. So that's why these disadvantages are removed in complementary symmetry power amplifier. Means in complementary symmetry power amplifier, both the transformers are avoided. Meaning thereby no transformers are used for input as well as at the output. But instead of that, two transistors are used in such a way that out of two transistors, one is NPN and other is PNP. But as far as in class A, class B and class AB push-pull power amplifier, both the transistors are same, either NPN or PNP. But in this case, one of the transistor is NPN and other transistor is of PNP. But it will work same as that of push-pull power amplifiers. If you look to the circuit diagram of complementary symmetry power amplifier represented here, it is symmetrical in upper half as well as the lower half. If you divide this circuitry at the center here, this is the lower half, whereas this one is the upper half. They seems to be symmetrical with each other. So that's why it is called as a symmetry power amplifier. But as one of the transistors is NPN and other transistors are PNP, the working of NPN and PNP transistor are opposite to each other. In short, we can say the working of NPN transistor and working of PNP transistor are exactly complementary to each other. Meaning thereby, when one transistor conducts, other transistor will remain off. When other transistor conducts, the first transistor will remain off. Such a working of transistors are to be treated as complementary to each other, and that's why the circuit represented here, it is called as complementary symmetry power amplifier. Such a complementary symmetry power amplifier now consists of, let us see its construction. It consists of two transistors. Say here, as per this diagram, we can say it is Q2, which is NPN transistor. Another one is Q3, this is PNP transistor. Emitter of both the transistors are connected to each other as usual, as like in push-pull power amplifier. Also, the base of both the transistors are connected to each other. This is not in class push-pull power amplifier. Means both the base of transistor Q1 and Q2 are connected with each other, and also both emitters are going to be connected with each other. To the base of both the transistor, the signal to be amplified or the power level to be amplified is connected. Whereas to the emitter and the ground, the load resistance is connected. It may be headphone, or it may be a speaker, or it may be simply a resistor. Means we are applying the input to be amplified between base of both the transistor, and we are obtaining the output across emitter. Hence it is called as a type of emitter follower circuit or voltage follower circuit. The biasing of both the transistors are adjusted by using the power supply VCC, which are connected to the collector of both the transistor so as to reverse bias collector base junction and forward bias emitter base junction respectively. This biasing is utilized to adjust the operating point of both the transistor at the cutoff region. We are well aware that when operating point of BZT is adjusted at the cutoff region, it will work in class B configuration. Such a circuitry, we can call it as it is complementary symmetry circuitry. Let us see now how this circuit works. Friends, when input signal to be amplified is applied to the base of both the transistor, as it is a varying signal, its polarity varies. Let us suppose the positive half cycle is arrived to the base of transistor, say here Q2, and negative half cycle arrives to the base of transistor Q3. But do remember, transistor Q2 is NPN and it is now getting the positive half cycle. So base is of P type and it is receiving the positive half cycle of the input signal. So that's why the forward biasing of emitter base junction is increased. Whereas simultaneously negative half cycle is reached to but same cycle is going to reach to the base of transistor Q3. But transistor Q3 is of the type of PNP. Its base receives again a positive half cycle with respect to ground. So that's why emitter base junction of transistor Q3, which is PNP, it is now reverse biased. At the cost of this, under this condition, transistor Q3 remains cut off. It doesn't conduct the current, collector current. Whereas transistor Q2 will conduct the collector current IC1 that passes through the load resistance. So direction of current that flowing is represented here. Whereas assuming Q3 is cut off, it doesn't conduct the collector current IC2. At the cost of IC1, the power will be developed across the load resistance, which is represented here. If suppose this is the input positive half cycle received to the base of transistor, then through Q2, as being its emitter base junction is forward biased, current flows, but at the same time through Q3 no current flows. Because of Q2, across RL we can get the power or current in this particular aspect. But when polarity changed, means when input becomes a negative half cycle, Q2 is now cut off, hence no current flows here, but at the simultaneously through Q3, as a being it starts conducting the current flows through that particular transistor represented here. Hence, through RL, across also the current that flows. Thus, when polarity is reversed, for negative polarity, transistor Q3 conduct, for positive polarity of the half cycle, transistor Q2 current conduct. When Q3 conduct, collector current IC2 will flow through the load resistance RL, and because that, suppose base of both the transistor will receive the negative half cycle with respect to ground. When it receives the negative half cycle, as a being transistor Q2 is NPN, its emitter base junction is reverse biased and now it doesn't conduct the current. Hence, IC2 doesn't flows. But simultaneously, base transistor Q3 is PNP and it is going to receive now negative half cycle at the input. That's why Q3 is forward biased. Hence, collector current will flow through transistor Q3 in the lower half of RL. Thus, as a being, direction of current flowing through the load resistance are opposite to each other, the difference in collector current will always flowing through the load resistance and that will develop output power across the load resistance. All this makes you aware that when Q2 conducts, then it pushes the current to pass through the RL. At that time, Q3 doesn't conduct. It pulls the current back. But when Q3 conduct, it will pushes the current to flow through the RL. But at that time, Q2 doesn't conduct and it will pulls the current back from the RL. Here also, one transistor pushes the current, other transistor pulls the current, but working of both the transistors are complementary to each other, whereas circuit seems to be symmetric with each other, and that's the reason why this circuitry is called as complementary symmetry circuit. And as a being, it is used to amplify the input power level to produce at the output. It is called as complementary symmetry power amplifier. Friends, it is the type of power amplifier which is used in many of the systems, especially to drive the speaker, to drive the headphone. Also, it is used in operational amplifier as a last stage to deliver the maximum power in integrated circuit. So, wherever more power is required to be obtained to drive the load, in all these places, the complementary symmetry circuit is being widely used. Friends, do remember that it is a type of circuitry which is more simpler than that of the what we can call it as Class A, Class B and Class AB push-pull type of amplifier. It works same as that of push-pull power amplifier, with the difference that here no two transformers are used, hence weight is reduced and its cost is also reduced. Friends, that's all about the today's lecture, that is complementary symmetry power amplifier circuit.